Good afternoon, Professor.
Good afternoon. Thank you. Hey,
Good afternoon, Professor.
Good afternoon. I love it. I love it. Thank
Good
you.
afternoon, Professor.
Thank you, Savannah. I mean, good afternoon, Amy. Good afternoon, Caroline. Good afternoon, Savannah. It should not mean so much to me, but it does. Good afternoon. I mean, it shouldn't mean so much to the class, but it does. Good afternoon, Amanda. Good afternoon, Caitlin. Good afternoon. What did I just say? Caroline, Savannah. Good afternoon, Shamil, Elda. Okay, wait, I'm doing the chat now. But it does make a difference, doesn't it? I mean, it just doesn't it? I mean, it's hard for us all to come. Doesn't it just make it a little bit easier once we get here? Okay, good afternoon, Kevin. Good afternoon, Alicia. Wait, more people coming in. Sorry. Good afternoon, Amanda, because I'm doing the chat now. I know I said that, but okay, good afternoon, Jamalette. Hi, Christina. Good afternoon, Caitlin. Good afternoon, Kimberly. Good afternoon, Sophia. Hello, and good afternoon, David. Oh, that counts as two, right? I mean, okay. Good afternoon, Felicia. Good afternoon, Chloe. Good afternoon, Adon. Good afternoon. Wait, I just missed something. Good afternoon, Adon. Good afternoon, Shamil. Good afternoon, David K. Good afternoon, Samuel. Sam A. All right. Well, all right. I think that's everything. Good morning. Good morning. Good afternoon. Good afternoon. Yes. Oh yeah, Kevin still got the Halloween thing going on. Samuel still got the rose. Oh, and Shamil has, we're like so floral in this class. It's beautiful. The contrast between the Shamil thing and the Samuel thing, I mean, the literal visual contrast is actually, I should rearrange the squares just around that. Okay, sorry. Good morning. Also, if any of you are ever thinking like, God, like his enthusiasm is like a little pukitating, like, I mean, it's physics class. Like I barely drag my feet in here. Like what's with all the ridiculous enthusiasm? Don't be fooled. I'm trying to fool myself as much as, I mean, it doesn't come easy. Like the best way to be enthusiastic is to be enthusiastic. You know what I'm saying? Like people spend the rest of their whole lives trying to think themselves into right action, but it's actually a lot more effective to act yourself into right thinking. You know what I'm saying? Fake it till you make it. Okay. All right. I'm just teasing around. Okay. But hello, everybody. We're just going to get going. We're actually making tracks here, sort of. Oh, I have to put up something. Okay. What we're going to get to, I'll tell you right now, I'm just getting my head together. Of course, stop me at any time. This looks like a complicated board here. It kind of is. In fact, wait, did I? Oh, wait, there's a symbol missing. Hang on one second. I'm sorry. I don't know how that happened. Okay, now it's right. Yeah. All right. So as usual, the board is always meant to be some sort of glimpse of, I mean, the first board is always supposed to be some sort of glimpse of like where we've been and where we're going. And kind of, sometimes it's a little bit more where we've been. Sometimes it's a little bit more where we're going. Today, just to let, and this is also impossible to read. That's supposed to be an S. It's supposed to be a U, right? Just so that you know. I mean, I don't know. If I looked at this, I might be a little bit intimidated. I'm not sure. Just so you know, the main thing we're going to talk about today is that big old duck problem. That like the very last problem of the big old duck assignment, which in theory is due today, whether, wherever you are with it, we're going to talk about that very last problem today. And you're hopefully going to see how it's putting together concepts from one-dimensional kinematics, from constant acceleration topics and problems that we've been doing. It uses concepts from lab 3, i.e. the constant acceleration due to free fall. Right, so that's a big part of the big old duck problem, but it also gets into what happened in lab 4. Yeah, it gets into what happened in lab 4 that I want to get into today, which really it transitions us to the next big topic. Obviously, the topics start going faster from here. They're always going a little bit faster and a little bit shorter. The next topic is in fact, let me just write that to make it absolutely clear. The next topic, like that big old duck problem, is the very all the problems prior to the big old duck problem on homework number 6, all those problems are the last group of standard problems that study one-dimensional kinematics, motion in a line within one dimension. And particularly the constant acceleration and associated equations that apply to one-dimensional kinematics. There, in theory, there's like no more of those equations now. In theory, even in principle, we have no new equations, no new information about one-dimensional motion or about constant acceleration. What happens now through lab 4 and through the big old duck problem is we segue into the two-dimensional world of a plane of two axes of space, right? An x-axis and a y-axis. We segue into that world. And when we go over the big old duck problem today, you'll see how we make that segue. But two main things to say about that. Actually, I'm going to say one big thing right now. Okay, so I'm going to turn the page. I'll go back to this page in a minute if you want. I'm going to say something conceptually about like introduction to two-dimensional motion, like right now on the next page. I will say this: what's on this page here, like presumably you should copy and all of that. And if you need more time, we'll flip back to it. But I want to warn you, especially people that are, like really paying attention in general or paying attention right now. It might look like what's on the page right here is a new set of equations. If you look really carefully, you will see that it's not a new set of equations. It is an adaptation of equations we already have. Like very specifically, the very first equation written here, y equals 1/2 gt squared plus v naught subscript y t, that is an equation we've been working with now and sort of practicing for a couple of days. Like that's just the equation, x minus x naught equals 1/2 at squared plus v naught t. It's just that. Only first of all, instead of x's, it's written with y's. Second of all, things like v naught has a subscript on it, a subscript y directly after it. And instead of a, I wrote g. So what you might understand if you're with me here, and this is again, we're just like taking a bunch of steps down the road of physics, and the kind of steps we're taking, again, like maybe this is not the way you're used to learning physics, or I don't know, but what we're trying to do is take the key steps that allow us to take steps on our own later in physics. Like, right, so what I'm trying to show you is now a thing that's happens in time, all the time in physics, which is we take an old equation and we just adapt it to a new context. It's not new information, it's a new adaptation. And we want to get increasingly flexible with that idea. And so in other words, all that's happening in the first equation that's written on this page right here, all that's happening is we're taking distance equals rate, we're taking the constant acceleration position function and we're adapting it to a y-axis of motion. We're taking Galileo very seriously. We're saying whatever's true of this axis is true of this axis. There's no, that's just a matter of how you hold your head. All axes, all coordinate systems, as long as they're not accelerated, all inertial frames of reference are equally subject to the laws of physics. So anything that we believed about this, we would believe about this if we just turn our head, right? We believe about this. And when you're moving in one vertical axis under the influence of just gravity, we call that free fall, we've been saying. So we put a bunch of y's in the equation instead of x's. We put a little y subscript after the v naught to make it explicit to ourselves that the v naught we're talking about is v naught in the y-axis, like the initial vertical velocity is what we mean by v naught now. And we make it explicit to ourselves that what's the acceleration in the y-axis? Well, it's that acceleration due to gravity that we started calling lowercase g last week, right? So it's sort of just like a substitution or, or an adaptation. So that first equation I'm saying is just our old equation, but now applied to one axis, the vertical axis. It's totally what we are going to use when we solve the big old duck problem, because the shot that and I'm assuming you've at least looked at it, or that hopefully maybe you could be looking at it right now in front of you. The last problem of homework 6, someone shoots something up and then, someone shoots something up in gravity. It goes up, but it's still totally free fall because from the moment it's released from the gun or the slingshot or whatever, it's just traveling on its own laws of physics. No one's pushing it, pulling it, touching it, blah, blah, blah. So something is free falling up. So that equation applies. Then I guess I'm cutting to the chase here, but just so you understand, then the next equation there, and I will explain this more in detail when we start solving the problem explicitly in a moment. So much for my turning the page, but the next equation looks like a new equation. I mean, you should write it down now if you're taking notes and you're trying to follow what I'm going to be saying about the problem. But I want to caution you, that is not a new thing to memorize. It's not new information, and it's not something you should memorize as such. You might even recognize the form of it. I almost want to stop class and ask you, but I feel like I'm like in a nested loop of a nested loop, so I won't. That T thing, look at it for a second. I'm not going to, I mean, if anybody wants to put in the chat, I'm not going to like literally stop us, but if anybody wants to put in the chat or shout out or anything, like where I got that crazy looking second equation, like it does look totally new for a physics class, but it might be sort of recognizable from a math class. That second equation on the page, you have seen something of that form before. I mean, I'll give you a big hint. If anybody, I'm not going to, again, I would love it if anybody wants to put something in the, yeah, dude, yeah. Oh, do I love this class? Okay, I could, oh my God, that's like 4 of you. And anybody, I'm not closing the door. If anybody sees what's going on right now, even though other people are writing, yeah, write it. If you even agree with them or you know why they're saying that, it doesn't matter whether you're the first person or not. Please, I'm so thrilled that at least 5 people, 7 people, awesome. And some of them are going direct and some of them, God, I mean, I know if this were actually a podcast or whatever, or like a something like nobody would watch it besides me, but I would totally watch this. I'm so thrilled. Look at that. That's 11. That is 11 people in the chat. Just, some private, which is totally fine, but including all the private people whose names I won't mention, that's 11. You guys and your math professors should be proud of you. Yes. You are absolutely right. That thing right there totally is. And you should also check if I did it wrong. I mean, I don't think I did, but check. I mean, what I'm doing there, you're absolutely right. And sorry, I'm partly excited that you guys are good and that you're so with me. Seriously, I'm not faking that. I mean, I'm faking the general psychological energy that I have today, but boy, did you help it. It's exciting that you recognize that. It's all, and yes, like in other words, what I'm doing is I'm just noticing that y as a function of t is a quadratic function of t. That y is a second degree polynomial in t. And so that if for some reason I wanted to solve for t, which it turns out in the big old duck problem I do, if I wanted to solve for t, I'd have to do more than just like subtract a term from both sides or something, because I got a t squared in there and I've got a t in there. So to find t, I'd actually have to find, so to speak, the roots of that equation, right? Like in other words, well, so I have to actually do the quadratic formula or something like it, or difference of 2 perfect square. I mean, I don't mean that. I mean, or completing the square, which is where the quadratic formula comes from in the first place, or like use a graphing calculator or something. But yes, if you're noticing that that's the quadratic formula, which yay David, yay Savannah, yay Christina, yay Amy, yay direct chat person, yay Caroline, yay Amanda, yay another direct chat person, yay Caitlin, yay Felicia, yay Samuel, like seriously, if you recognize that, then you realize what I'm doing right is like, that's the way or a way to solve for t, given that y is a quadratic function of t. And then yes, what I think you're realizing, if you recognize that, is like instead of putting in the a, like instead of saying minus b plus or minus the square root of b squared minus 4ac all over 2a, which is what the quadratic formula is, I like literally I decided, okay, what's a? A is 1/2 of g. What's b? B is v naught y. Like I'm assuming all those people that said that basically follow that. But anybody who didn't say it, right? Like they're saying, okay, like we have a quadratic. Oh, and in fact, I did make a mistake because technically, wait a minute, technically y is negative. Hold on. Really, technically, that quadratic expression is 1/2 gt squared plus v naught t minus y all equals 0, right? So technically C is negative. So in fact, right? Stop me if you don't follow that. So minus b minus plus or minus square root of b squared minus 4ac minus 4ac. Okay. So really I should make this a plus. Yeah, you should. And that's a little confusing too, because I also notice I haven't actually defined. Oh no, you know what? Wait. Hold on. Don't do anything. Don't anybody do anything yet. I know what I want to do. Just to make this, before I go any further and confuse anybody anymore. Right. Okay. Just to make this totally clear. Okay. I'm getting ahead of myself, as I sometimes do, but I'm just sidebarring right now to say, so this is all in the context of big old duck. I'm going to make the decision that up is called positive and down is called negative, and G is just that number 9.8. So I just put in negative signs to adjust to make this totally precisely right. But anyway, back to the program. Yes, I'm looking at the equation and saying, okay, this is a quadratic. So it's really technically negative 1/2 GT squared plus V naught T minus Y all equals 0. So then I can multiply everything by negative signs. And I can say, and I can say that A is negative G over 2. I could say that B is V naught Y, and I could say that C is negative 1. I think you're all following that because you all made the recognition. So anyway, what I'm saying ultimately is that T expression is a way of solving for time in a situation like this, like in the big old duck. And that's what we are going to do in the big old duck. It's not just meant to be a waste of your time. But it's not also meant to be something that you should memorize. It's just an application of the equation and an application of quadratic formula. And quite frankly, one of the reasons I am excited that you all made that recognition is, I don't know about you, but like I went through months and months and months in my life, like learning the quadratic equation or the quadratic formula, whatever you want to call it. And like, I hated it, of course. I mean, I didn't see, like, what's the point? Well, it turns out there is a point. I mean, for me, this was one of the first times in my life when I saw like, oh, wait, it actually like, it's useful and does things. It does. It really does. And the proof of it from completing the square is actually kind of interesting. So I'm excited if we could see the quadratic formula a little bit alive here. We will. It's not meant to be a new memorizer. It's meant to be like, this is how physics works. Now also, and I will move on and turn the page in a second. Sorry, I'm totally doing an imitation of myself here. But then you notice underneath it says X equals V bar sub X times T. So what's that? Well, that again is just an old equation. That's displacement equals average velocity times time, or average velocity is defined to be displacement per time. For both of these equations, if it helps you at all, I'm making assumptions here, just like I assumed that up is positive and down is negative. I'm also assuming that X naught is 0. And I'm assuming that Y naught is 0. So I'm using Galileo. I'm making decisions about how my coordinate system looks. But then with that, then I'm adapting old equations to new concepts or to new situations. And I'm trying to get increasingly flexible with that and not be bothered that I don't see an X naught in the thing, or that I now see subscripts in the equation. Now, last word on this, and we really will turn the page. You'll notice, I mean, this is all about big old duck. So again, if you've done it, then you know what I'm talking about. If you haven't, you might at least want to be looking at the question right now so you follow like why I'm speaking of this in abstract. Big old duck is our first actual problem in the homeworks that, much like lab 4, is a two-dimensional problem. There's 2 dimensions of space being referred to and being involved in big old duck. In big old duck, you've got a duck going across the top of the sky and like this or like that. And then you got this guy shooting up to the duck. So there's a y-axis and there's an x-axis. The thing that I'm just trying to say on this page that I want to break down for you on the next few pages is that can, maybe even should, look intimidating at first. Like, wait, suddenly we have 2 dimensions going on here. Just like lab 4, you shot something off a lab table that went forward, but also went down 2 dimensions. So it does legitimately raises the question, what do we do when we have 2-dimensional motion physics? Like, we never studied 2-dimensional motion before. Do we have new equations to handle 2 dimensions of space? And the ultimate answer is no. The ultimate answer, it all has to do with this phrase at the bottom of the page, independent yet simultaneous. I'm now finally going to turn the page and say what I mean by that and put this together. But the short version of it is, notice that the equations in the middle of this page are just old 1-dimensional equations, but they're being adapted to 1 dimension of space at a time. Like, the first 2 equations on the page are just an old 1-dimensional equation, but it's being adapted to the y-axis of space. And then the equation below it, below the 3 marks, is an old kinematic equation, but it's being applied to or adapted to the x-axis of space. And that's what we do from here on in physics. We don't invent new knowledge or new information. We take the old information, we adapt it to 1 coordinate system at a time, Galileo Galileo. So what I mean specifically is this. Okay. Now, here's a truism. Okay. Now, again, this is all in the context of big old duck, the problem, which we're about to, for the rest of the period, we're going to analyze the big old, or solve the big old duck problem. But the point of the big old duck problem, like lab 4, so let's see. The point of the big old duck problem and the point of lab 4 is to get us into 2-dimensional motion, which is really to say any higher dimensional motion. It's to get it into kinematics in any number of dimensions higher than 1, n number of dimensions. Okay, and here's how we deal with higher dimensions of physics is we take Galileo, the principle of relativity, the whole thing from the train of thought, the whole idea from the belief that the earth could possibly be moving and yet we wouldn't feel it. The whole original idea of Galileo is that the laws of physics are the same in all unaccelerated coordinate systems, in all inertial reference frames. And then we've had these other extensions of that, right? That was form number one. And then we had form number two, which says that you can't do an experiment to find out the velocity of something just by itself in space. So then we had form number three that said, well, then fine, then if you can't do an experiment to do that, and this is physics, an experimental science from here on in, then if you can't do an experiment to find out how fast and what direction something's going by itself, in and of itself in space, you can only find out how fast and what direction something's going in a given coordinate system, in a given frame of reference or perspective that is compared to some other object. Then we said form number three, okay, all velocities are relations between every velocity is a relation between one object and another object, or one object and an established coordinate system built around another object. Every velocity is relative to some basis of comparison, some frame of reference or second object, same thing ultimately. So we said in form number three, all velocities are relative, are relations, not of two objects rather than properties of one object. Then we said in form number four that velocities are so relative and so keyed into frames of reference that even when you're adding velocities up, you have to add them up according to frames of reference, and you have to add them like vector quantities that have magnitude and direction. Now we're going to say, well, what if those vector quantities, what if those magnitudes and directions are like in more than one axis of space? So we say now, well, each axis of space is its own little coordinate system, like the number line that we've been living in for the last month and a half of this class, that x-axis that we've been doing all of our physics in, that's a coordinate system. The laws of physics apply to it completely. The laws of physics equivalently and correctly also apply to some other axis, like the y-axis. So if you put the two axes together, here's the key conceptual point. Again, this is just another extension of believing that the earth moves. The minute you're willing to believe that the ground below your feet could be moving all the time at 65,000 miles an hour relative to the sun, and yet you would never feel that or be bothered by it or incorporate it into any of your calculations, the minute you actually accept that idea, then what physics is saying is then you accept all of these implications, one after another after another. Each new chapter of physics is another implication of just saying the earth is moving. And so therefore, all of these things, and yet we can not feel it. So all of these things follow from that. And the thing that's following today is that any time in physics, from here on in, we want to solve a two-dimensional problem, or we want to analyze a two-dimensional experiment. In fact, even better, we want to solve any problem or any experiment that's in n dimensions, any number of dimensions you name, 2, 3, or if there's 4 or 5 dimensions, 4 or 5 dimensions. What we say from now on, that any n-dimensional problem we face is actually just n one-dimensional problems occurring at the same time, but independent of one another. That is actually, okay, and again, I'm being too abstract as usual. I should just get to the concrete example. I realize that, and we will, but the abstract point, the general point that I'm going to use to solve this concrete problem is that as long as I know all my equations that apply to an axis of space, which we now do, then you throw as many axes of space at me as you want and say things are happening in all of them at the same time. And I'll say, okay, things are happening in a bunch of axes at the same time. Still, the laws are applying to each axis one at a time. This is what I mean by independently. I mean, what's happening in the x-axis doesn't directly affect what's happening in the y-axis. What's happening in the y-axis doesn't affect what's happening in the x. That's two distinct coordinate systems that are each just playing out the laws of physics
So the laws of physics and the equations will play out on the x-axis. The laws of physics and equations will play out on the y-axis. They won't affect each other at all. We could do two separate columns of equations. That's what we're going to do. But then just say, but they're all happening at the same time. That's what makes this a two-dimensional problem. So in the big old duck that we're about to analyze, or in lab 4, you have things happening along two axes at the same time. And it's very important to so in the lab, you have something that's moving forward, but that very same thing at the very same time is falling down. So we recognize this is happening at the same time as this, as the down. So whatever t that we solve for or know about in one axis will be the same t that will apply to the other axis. The link between the two axes from here on in life, this is the truism, the principle. If you have a two-dimensional problem or an n-dimensional problem, the link between and among all of the axes is t, the time. They're all happening at the same time. But the problem solving, the equation application, substitution, all that stuff happens at each axis independently. It's its own little world of physics that happens to just be pressing forward at the same time as all the other worlds of physics. That's how we're going to solve, and that's a truism for so how we do multiple dimensional physics from here on in is we just do a number of one-dimensional physics problems. We solve them separately and independently, but we realize that they're all happening in the same t. Okay, all right, that's like the overview. So this is Galileo's principle of relativity, form number 5. Every n-dimensional experiment or problem is in fact n one-dimensional experiments or problems occurring independently yet simultaneously. Okay, so let's see how that plays out in the big old duck problem. Okay, I'm moving on finally. Sorry, and it's like 1:39,000 o'clock. No, it's 12 hours. Okay, all right. And I think I have to pull this up on the screen. Pardon me for a second. Just pulling it up. Bear with me for a second. Or maybe someone knows in the chat. It's okay, this is problem 6, right? Okay. And by the way, and note it, I'm just saying, this is not, I'm just noting that because I'm as behind as you can still totally do it. No penalty. I still owe you a bunch of things. I say this every time. It's life in complicated times, but I just do want to recognize, I totally recognize and appreciate and note that if your name just happens to be Chloe or David K or Caitlin or Amanda or Kevin or Caroline, it's totally noted and appreciated that you totally killed yourself to get this thing in on time. And it may have been a stretch because it was like a long, big assignment. So it's totally noted. I'm just saying, I'm not criticizing anybody else. I'm just saying, thank you very much, you 6, because I totally get it. And I see you, so to speak. But now, all right, but that's such a risky thing for me to do, I know. But so one quick thing, and then I'm gonna start, but I am gonna start going over it right now. So those people definitely, hopefully they have some thoughts to follow along. Like they have the advantage of having thought about it in advance. So maybe what I'm going to say now is going to make maybe more sense or land at a different level for them, right? But if you're anybody else in the class, this is not a criticism. Honestly, this is not sarcasm. This is not shame. This is just, I'm now going to be talking about something that may be a little bit slightly more abstract to you. So please, please, please take a moment, first of all, and look. And don't get wrapped up in the fact that I'm now talking about something you haven't done. That's not what this is about. This is just about knowledge. So take a moment to just look at the question now. It is not too late at all. See if you can understand what the question's asking, blah, blah, blah. And then and then follow me along when you actually turn it in. Of course, you can benefit from whatever I say here now, but think about it as something that, and all of you, with 6 and 12 of all of you, like, I know I keep postponing this awful issue of like that we have to have an exam or something like that somehow, and it will be friendly. It won't be a fun experience, but it will be a friendly experience. And this problem will be on it. I'm just like, it will, like with different numbers or whatever. So whether you've done it or not, just like pay attention to it as something you do want to know. And don't be ashamed. I'm going to start, we still have 40 minutes, right? So I'm going to start going through it. Certainly, if you've already thought about it and you find out that you've made errors or whatever, obviously you should stop me, and or you don't understand something I'm doing, or you have a different way. Please put in the chat or the direct chat, something to that effect. But at the same time, even though, yes, of course, I'm slightly praising like 6 people who are, it's not that everybody else is behind. It's that those 6 people are ahead, okay? And they're ahead of me because I'm behind, okay? So, but even though I just praise them because they should know that, all the rest of you, this is not one of those times where now when I'm talking, you should be like, well, I can't say anything because I haven't done the thing yet. Like, it's just going to make it clear that, Nick, no, try to follow me. And when you don't understand what I'm saying, like, do please, if you want to put in the direct chat, it's fine. But I'm talking to all of you. I'm talking with all of you. All of you can still rock physics and get A's. Like, seriously. Okay. Like, this is physics, but it's group therapy too. Or maybe it's therapy for me. So we're about to go over the big old duck. The class is for you in different ways, whether you've done the problem or not. That's for real. But now, just as I'm saying all that, I'm just doing one quick thing and then I'm going to start. Hold on. But yeah, like, look at what you're either thinking now or you. Okay. Okay. All right, so here we go. So I'm now going to start talking about the problem. So this is, homework 6, problem 6. Now, boy, I definitely need a diagram for this, right? And I definitely cannot draw ducks or humans, but we definitely need to know. I mean, this is, so I'm going to draw a diagram. First of all, I'm going to say, all right. This is 2 dimensions. This gets us into some issues now. We have to be very careful about this. So I'm going to say, first of all, now I've right. So, and again, I'm looking at the problem. Maybe I can, I don't want to switch screens. Like, hopefully you're looking at the problem. Oh no, I'll follow. I'm sorry. I'll follow I just saw that there is a diagram in the thing. I'll follow. Okay. I'm going to follow the diagram in the thing, but I have to make my own diagram because I'm doing homework. I'm doing a exam, and this diagram is super important, right? Like, I mean, because this is a confusing problem. I mean, the diagram is going to label the numbers and the terms, but more than that, even before it labels the numbers and the terms, the real purpose of this diagram is to label the coordinate system. We're really starting to take Galileo seriously now. Like, we have to make choices about our perspective, our reference frame, our coordinate system on things. And especially now that we're in 2 dimensions, let's get it straight. like according to the diagram that's given in the sheet and the reference frame that I'm therefore choosing to adopt, like south is to the right, north is to the left. Now, first of all, that's a legitimate choice. There's a reason for it. You could do something else. You could make north to the right. You can make south to the left, but then you just have to be consistent with it. I'm then saying that anything that's going to the right, I'm going to call positive, like I'm looking at the sheet. Ooh. Yeah, okay. And even in the diagram, the diagram gives magnitudes, but it does not label pluses and minuses, which is kind of a weak. So I really need that in my diagram. So I'm trying to establish what I mean by positives and negatives and all of that. And before I go any further, like notice I'm saying south is to the right, north is to the left, and then I'm saying up is to the up and down is to the down. Like that would mean that east and west are coming out of the page and going into the page, right? Like east and west exist. They're just not playing a role in this problem, and they're just not being captured in my diagram. But please understand, you know, like north, south, east, and what north and south is an axis, east and west is an axis of space, and up and down is yet a third axis of space, right? When we talk about north, south, east, and west, the 4 points of the compass, we're talking about 2 dimensions on the surface of the earth. And then there's also the concept of up and down, which is how far away you're going from the surface of the earth or toward the surface of the earth. And like how you, just like Galileo, like we're focusing on 2 of those 3 dimensions here and putting them together in kind of an unusual way because we're allowed, because each axis is independent of the other axis, and the laws of physics work in each one. So long way of saying, do not confuse up with north. It's not the same thing, right? I mean, north means toward the North Pole on the surface of the earth. Up means away from the center of the earth. Up and down are along radii of Earth, and north, south, east, and west are along the surface. For what it's worth. Okay, now I'm making my diagram. I'm putting in the facts of the problem. Now I'm going to be a little bit more careful. In the diagram that's given in the sheet, there's a bunch of numbers given, but they're just given as numbers. There's no pluses or minuses in that diagram, which quite frankly, I think is a flaw in the diagram. But because there's no pluses or minuses at all, the diagram isn't making any claim about what's plus and what's minus. So I think it's missing information, but it's not making any wrong information. But I'm going to put the information in now, which is really one of the reasons that you got, you know, so it's as though there was no diagram in the given. I would still have to come up with my own. So I am going to make some information clear here. I'm saying that anything to the right is positive and anything up is independently positive. I guess, sorry, that's another thing I'm trying to say, is that the whole idea of plus and minus is how you designate direction on each one axis at a time. Each of these axes is its own number line now, with a forward direction and a backward direction, a positive direction and a negative direction. So so everything we've ever practiced on that big first homework that we spent forever on, because we were trying to get down these fundamentals, on the first homework called number line, we established it like there's a positive direction and negative. That carries over and now applies to each of our dimensions independently. Okay, so what I'm trying to say is in my diagram here, I got this guy. Apparently, I've got this guy that shoots something up at an initial speed of v0 equals 30. I'm going to be really clear and say like that's v0 in this y direction of up or down. This is the y axis, and the x-axis is the axis of north and south. So this guy shoots something up at an initial vertical velocity of 30 meters per second. I'm going to explicitly call that positive because I'm calling the positive direction up. Okay. Then so that's part of my diagram. Then I've got this duck. This duck apparently is going forward south at initially an initial speed of v0 x. I'm going to call it x. So I'm doing more than the diagram that's given in your sheet now. The duck is going forward at an initial horizontal speed of 20 meters per second. He's going forward, and then half a second after the shot is fired. So at
t equals 0.5 seconds, then suddenly the duck starts to accelerate, right? It already has that speed, but up until that point, like in other words, to be really clear, initially his acceleration was 0 meters per second squared. But then at t equals 0.5 seconds, the duck starts accelerating in the horizontal direction, a sub x, at a rate of 16 meters per second. But now I want to be really clear here. It says in the problem, I'm just reading it, you know, hopefully it's in front of you. Half a second after the shot is fired, the big old duck instantly commences a constant acceleration of 16 meters per second squared. Oh, forward to the, oh, it is forward. Oh, I'm used to a different, oh, that's funny. Okay, sorry. That's interesting. Oh, sorry. Okay, no, that's fine. But all right, forward at 16 meters per second squared. So I'm going to make that plus as well. Sorry, I was expecting that was going to be a negative for something because I'm used to a slightly different problem, but that's totally fine. So there's nothing wrong with this diagram. It's just incomplete. So I'm making that positive as well. He's going forward to the south. But now notice one last thing to be super clear. We now have two different physics problems happen. Oh, and sorry. And the question is, all right, let me back up. I'm sorry. So we've got this duck that's going across in the sky, right? And we got this guy, this human, this person down here on the ground. And the duck is over here. The person's over here. The person shoots. The duck is over here. The person here is here. And the person tries to shoot the duck. So the person shoots, fires the slingshot at some moment. So the duck is going along at that moment, and then almost in reacting to the sound or out of shock or surprise or response, like a half a second later, once the duck has realized that the duck has heard the sound, or half a second later, once the sound reaches the duck or something, the duck freaks out and starts going faster. Now that's maybe a stupid reaction on the duck's part. Maybe it should have turned around or something, but it doesn't. It just freaks out and starts going faster. So as of a second later, the duck is now accelerating along the horizontal axis. And our ultimate question is, given that acceleration of the duck and given that initial motion of the duck, like if we want to hit the duck, if we want the duck to be at that vertical dotted line, that is the extension of the human being's slingshot. If we want the duck to be at the right place at the right time to, in fact, be shot, then sorry, I'm totally, then where should the duck have been initially? Like, in other words, when should the guy, the woman, the person, when should the person shoot? When should they pull the trigger so that everything lines up and they actually get the duck? That's the question. In other words, like the diagram is showing, what we want to know is, what is this X such that the duck gets shot? I mean, this is like not an easy question. It's a little bit complicated. I'm looking at my screen right now, but I'll pause in a second. Really put anything in the chat if even the question, don't be ashamed if even this question has so much going on in it that you're not totally sure you understand the question. Also, I'm talking about it in kind of a convoluted way by accident. So don't be ashamed if you don't totally understand the question. Do realize, I hope you're starting to see with questions like this is why it's really important that step one of the 5-step method is make a diagram. Step two is write down what is the question, which I will do in a moment, because it's like, can be hard to extract from all of this. And then question 3 will be to start writing down general definitions and principles that we need. There's one other fact missing. Oh, no, I did write one other fact that I didn't mention, but is in my diagram, is that the height of the duck relative to the shooter is 40 meters, right? So we could say, in other words, Y, well, yeah, Y is given to be 40 meters, but we're looking for X. And just notice now,
Okay, we have two different sets of kinematic information going on at the same time. The duck has an initial speed and an acceleration that are of certain values. The shot that's being shot up has an initial speed or initial velocity and an acceleration of two totally different values, because the shot is subject to gravity, to free fall. The duck is not. The duck is flapping its wings and doing something in the air to make itself go. It's not free falling. It's exerting forces on the air, which are exerting forces back on it. The shot is free falling. So the acceleration, given all my positive and negative sign decisions, I just want to make it clear that the acceleration of the shot is pointing down at what we call the G value, or approximately 10 meters per second squared. So the acceleration is negative. Everything else is positive. Okay, I'm too much setup. All right, so that's the situation. So we've got our step one here with the diagram. We've got the question is, okay, so the question is, what is X? How far back was the duck or when the guy shot, or at what point in the duck's motion should the guy or the woman shoot? And again, it's assuming that until the shot occurs, the duck is always going 20 meters per second, constant and positive in the south direction. All right, it's been too long. Let me just look in the chat to see if there's any. Oh, chat. Okay, sorry. Sorry. Okay, good. Oh, yeah. No, absolutely. So one person in the direct chat just asked, no, I can't emphasize this enough. Absolutely. You can not only submit the homework after today, you can definitely resubmit it. Yes, please. If you learn, and I'm thrilled that someone's already asking this, because I feel like I haven't really said anything. And if I've already said something that helps you or makes you realize that you did something wrong or imperfect, you definitely can resubmit. And to everybody, again, say you already did it. Say you're one of the 6 people that did it. All I ask is, if you do resubmit, just like re-upload both. Like leave and you could just tell me, just only grade the better one. It's fine. But for me to see that you did both, and to remember that you did one super on time, is just good for both of us. But so yes, you could definitely resubmit. And those of you who haven't done it, you definitely can do it based on what I'm about to say for 22 minutes. I hope that's clear to everybody. But yes, good question in the direct chat. All right, so here and I'm sorry I'm over, but I feel like I'm being so abstract today, but that does make me feel like I've said something that might have helped. So that's good. So the question is, what's X? Where was the duck when we shot? So I'm going to start solving now. Okay. So that was step 1 and step 2. Just to be clear. So sorry, just to be, as long as I'm being this. So this is all step 1. Diagram and fact pattern, very important in this problem. I don't see how you could do this problem without. And yeah, the diagram in the sheet was better than I thought, but it's still, you got to do, okay. But I don't even realize that until I go through my own exercise of trying to do mine, right? And then step 2 down here is the question. What is the question? All right. Okay. So now we're going to the next page to step 3. GDP. Okay. The first GDP I'm going to say, I'm going to try not to drag it out again because I already made a big deal. But the first GDP is GPR form number 5. This is a two-dimensional problem. This is a two-dimensional problem, right? A two-dimensional problem is really 2 one-dimensional problems occurring independently. Yeah. Okay, so this is a principle. We got 2 one-dimensional problems happening here. Okay. What does that do for me? two things. One, it means that I can use all my equations one dimension at a time. That's what I'm going to do, like I sort of foreshadowed on the first page of today's notes. But to cut to chase, so independently means I can use my equations one axis at a time, but simultaneously means that all the equations are happening at the same, all the physics is happening at the same time. So what this means is, so what this principle means is that to solve this problem, we want to solve this problem. We want to know where the duck initially was so that the duck arrives at a place which is the same place as the shot arrives at the same time, right? For the shot to hit the duck, what we're looking for is the shot and the duck to be at the same place at the same time. Like that would be the solution to this problem, is what do we have to do to get these two particles to occupy the same position at the same instant? That's what this problem is asking. This is a classic physics problem. Now, I'm not saying it's easy, but I am saying it is not an, it's not easy, but it is simple, if you know what I mean. So let me be more specific. I'm saying that the amount of time that the shot takes to get up to the height of the duck must be the same amount of time as it takes the duck to travel from wherever it initially was to wherever it gets. So I'm saying, okay, I have 18 minutes. We will solve this in 18 minutes, but I'm saying I think this is our hardest problem so far. This is a real physics problem. Like, I'm not trying to make it any harder than it is, but if you looked at it and you went, ugh, and you like couldn't even start it, or felt you couldn't start, or you did start and you went off, like you wouldn't be alone. It's intimidating. It's intimidating to even to know how to start. But what I'm really trying to get everybody to see one day at a time here is that there is always a way to start, even when you don't know how to start. And particularly if you don't know how to start, what you want to do, you want to do the 5-step method, and you want to look for what this is saying is that the idea is that two dimensions happen at the same time. And that's a very big hint, because once I write down, okay, this must happen at the same time as this, then that gives me a big hint of what to solve for first. What, like literally, if I'm trying to figure out what to do, what I'm going to do is solve for the amount of time. First I'm going to solve for the amount of time it takes the shot to ascend 40 meters. Because that's something that I don't know, it's not given in the problem, but it's totally knowable. It's totally solvable. Like if I break this problem down to two one-dimensional problems, I have something that's being shot up at a given initial velocity in a given constant acceleration due to gravity, going a given displacement. I have displacement, I have initial velocity, I have acceleration. The only thing that's missing is time. I've got an equation for that. I've got not like, that's what we've been practicing. Like if I had said to you, how far does, if I'd given you others, if I'd given you the initial velocity and the free fall acceleration value and said, how high does something get if it's shot up at, oh, in fact, I'm looking at the time, we almost should practice this. But if I say to you right now, something is shot up near the surface of the earth, if I say that near the surface of the earth, the free fall acceleration due to gravity is -10 meters per second squared, if I could say to you, and you want to be able to do this by the time of the exam, if I say to you, shoot something up at 30 meters per second, how high will it get? oh, you can figure that out, right? If I shoot something up at 30 meters per second and it's accelerating down at 10 meters per second squared, and if I ask how high does it get in a certain amount of time, or frankly, even if I just say how high does it get, you could get that. And you can even get it in your head if you're really starting to practice what I'm saying here. But okay. So if I shoot something up at 30 meters per second, like you can know it's good at 30 meters per second. It's going to go slower and slower and slower to 0. It's going to decrease its amount of speed by 10 meters per second every second. So it's going to go 30, 20, 10, 0. So you would know in your head, it's going to take 3 seconds before it gets to the top. If I shoot something up at 30, it's going to take 3 seconds to go up to the top. On average, it's going to go 30 plus 0 divided by 2 is 15 meters per second. So if I shoot something up at 30, it's going to go for 3 seconds, an average of 15 meters per second. It will go 45 meters if I shoot something up at 30. You want to be able to, I'm not saying you did just do that in your head, but eventually you can do that in your head. Something that you shoot up at 30 goes 45 meters. Something that you shoot up at 40 goes 80 meters. So that was the chart that we finished right at the end, or badly, but that I posted at the end of class last time. And once you get used to that, you can do that in your head. But if you can't do it in your head, oh, and thank you, person who closed the circle of conversation in the direct chat. Thank you. That's points. If you can't do it in your head, what I'm just talking about is ultimately what that equation, x equals 1/2 at squared plus v naught t, does for you. Long way of saying that's all we have here. It's just that here the missing variable is t. All the other variables are known. So we can solve. So that's what we're going to do. If I can solve for the amount of time it takes something to go up, if I can solve for the amount of time it takes something to go up to a height of 40 meters, then that's the amount of time that I need the duck to travel for. And if I just find out how far a duck at a certain speed would go in that amount of time, I'm done. So that's what I'm going to do. I'm going to solve for the time. So my program is first solve for the time. Okay, so here we go. So how much time and well, so I'm saying y equals 1/2 at squared plus v naught t, like y naught is 0, right? So y equals 1/2 at squared plus v naught t. So I'm going to do it out. So y equals 40 meters. 1/2 a is -10. T squared is what I'm looking for. V naught is 30 meters per second squared plus t. Okay, so I'm just doing this directly now. The thing that I put at the front of the page summarizes all this, but I'm doing it directly, concretely now. Okay, so, right, so 40 equals -5 t squared plus 30t. So -5 t squared plus 30t minus 40 equals 0. Right now I can divide, I'm going to make this as simple as I can on myself. Now I'm going to divide both sides by -5. So I have t squared minus 6t. I'm dividing both sides by -5 to get rid of the negative signs and everything. So plus 8 equals 0. Now I could use the quadratic formula like I did on the front, right? I could say t equals -6. So plus 6 plus or minus 36 minus 4ac. So minus 32 over 2. Right? Or I could factor, but I'm just trying to be consistent with what we did on the front page. So plus 6 plus or minus the square root of 4 all over 2. So 6 plus or minus 2 all over 2. You know, the next page, so 6
Okay. We have 9 minutes left. Okay. Okay. No, wait, we're not done yet. We still have 9 minutes, right? We're not done with the answer yet, but we're almost done. We did the hardest part. We got what we have here is the amount of time it would take for the shot to get to that level of the duck. And now what we have to do is say, okay, how far would the duck go in that time? However far the duck would go in that time, that's where it should be when we fire the shot, and we'll be done. So I'm going to do that next. Now, just so I can get answers to the problem and wrap this thing up. So that was all the y-axis. Wait, that was the y-axis. Now we independently go to the x-axis. We're going to now analyze the x-axis independently. In the x-axis, we're solving for x now. We have everything else. In the x-axis, well, all right, in the x-axis, for the first 0.5 seconds, the duck is going constant velocity. So it would go at its average velocity of 20 meters per second. And it would do that for 5 seconds. I'm doing this a little bit fast because, I want to finish this. But first, the duck would travel in the first 5 seconds, it would travel 10 meters. So the duck has to at least be back 10 meters, no matter what, for us to hit the duck. Like no matter what, the duck is traveling 10 meters in the first 5 seconds. But then there's more time. How much more time? Either 1.5 seconds or 3.5 seconds. Because we got 2 routes to the first part. I'm going to explain the 2 routes in a second. If you believe me, I will. I'm just trying to get an answer first. So for time, we got 2 possible times. I'm going to use them both. The duck is still going to travel for either 1.5 more seconds or 3.5 more seconds, because it travels for a total of either 2 or 4 seconds, right, according to the calculation we just did. So let's try right. So I'm subtracting. It travels for definitely 0.5 second before it even accelerates. But now we're going to accelerate. So it accelerates at a forward rate of 16 meters per second squared. And it does that for 1.5 seconds more. Oops. So 1.5 times 8 is 12 plus 30. So answer 1 to this problem, and there's 5 minutes left. Answer 1 to this problem is that we should fire. Answer 1 is fire when the duck
is 52 meters north of you, right? My answer one is, in other words, 42 meters I got from the equation for acceleration. And then I added 10 more meters to it because we already said the duck's already going 10 meters even before it even accelerates. So it goes a total of 42 meters plus 10 meters, 52. Or the other time, x equals 1/2 16 times am I doing this right? Wait. Yeah. It's 3.5. Yeah. Oh, but that's supposed to be squared. Oh, I'm sorry. I'm going too fast. I knew I would do this. Hold on. That's 8 times. Okay, 58. Yeah. Okay. Or the other answer, which I'll get in a second. Bear with me for a second. We still have 3 minutes left, so just bear with me for a second. Okay, the other answer is 168 plus 10, so 178. These are the two answers. We have 2 minutes left. First of all, I'm saying the two possible answers to this problem is you should fire either when the duck is fit. And if I made a math error, you could check and tell me. I don't think I did, but if there's a computation error, then I apologize and you can tell me on Wednesday. But I say that the duck should either be placed at 58 meters to the north, or you should fire when the duck is 58 meters to the north, or you should fire when the duck is all the way back at 178 meters to the north. And there's still 2 minutes left of class. Bear with me for a second. So that raises the question, wait, why are there two answers? Oh, wait, I'm looking in the chat. I'm looking in the chat. Oh, good. Oh, yeah. Oh, thank you. I'm sorry. Thank you, Caitlin, and thank you, Caroline. I see that now. Yes, you're totally right. Thank you. But I think I fixed it. I think it's fixed now. But thank you. Yes. Good call. So these are the two answers, 58 meters and 178 meters. The big question is, why are there two answers? Why could you fire one of two different times or two different places? And the answer is because there's one of two different times that the shot would arrive at that height. And the answer to why there's two different times, and I'm sure many of you did see this, but I just want to make clear why we're getting two different possible times, each of which is valid for when the shot would arrive at that height is, well, mathematically, because it's a quadratic, so there's two roots to every quadratic. But what does that mean physically? Physically, it's because the shot is in free fall. It goes up, going slower and slower and slower and slower. And that's all the math knows and all planet Earth knows, that you shoot the shot up, it's going up slower. It gets to that height, but then it passes that height, eventually comes to zero, and eventually starts coming down. In fact, it was shot up at 30 meters per second, right? So it would, as we said before, if you think about it, after 2 seconds, when it's at that height, it keeps going for one more second till it reaches a peak height and then starts coming down and it's back at that height again. In other words, the math is either that ignorant or that smart that it doesn't care about the duck. It just knows that there's two possible times that a shot would arrive at that height, one time on its way up and one time on its way down. And we never said we needed to hit the duck while we were on our way up. We don't care. The bullet could be on its way up or it's on its way down. So if you want to hit the duck while you're on your way up, you put the duck back 58 meters, you shoot when it's 58 meters and it goes like this, shoot. But if you shoot when the duck is all the way at 178 meters, then the duck will be going like this and your shot will be going like this, then it'll come down and then boom, hit it on the way down. Two answers but it was just two independent yet simultaneous problems. That's it. there's a couple other questions on the sheet. I mean, but the answer is, well, I just answered B. That's why there's 2 roots. And C, if the duck had gone, had accelerated negatively, that's a very interesting question. There would still be only 2 roots. We could talk about that on Wednesday, but there's 2 answers to this problem, no matter what the acceleration of the duck is. But that is it. And thank you for being so patient and on every level. I'm done. If there's any questions right afterwards, but thank you, all of you who've done this and who corrected me. And I think those are the right answers. You can tell me if you got different answers. I will see you on Wednesday. You guys are great.
Have a good day, Professor.
You too.
Bye. Thank you.
Thank you. Oh, thank
Have
you.
a great day, Professor.
Thank you. Thank you very much.
Oh,
Good job.
Professor, would you post the notes on?
Oh yeah, I always do. Yeah, they'll be posted in 2 minutes. Yeah, they're always in Google Classroom right afterwards. Yes, you should look. Yes, absolutely.
All right, thank you.
Wow, thank you.
Bye.
Oh, and I'm stopping the recording. Oh, wait, Alicia, are you still there? Going once, going twice. Bye-bye.